Okay, good afternoon, everyone. We are going to continue 4.3 today. We are talking about how the derivative, in knowing whether or not the derivative is positive or negative or zero, tells you about where a function increases and decreases, and that helps us determine local minimums, local maximums of a function. So were there any questions over anything up to this point that I can help clarify? Everybody feels okay?
Just real quick, the date for the next exam, I know you said it's Thursday, but are you going to move it back if we don't get through enough topics?
I think I still want to keep it where it is.
Like, how many topics would you say we need to like learn before you say we're good to go on the exam?
I would say what we do today, and then what we do next week won't be on the exam. That'll be on the final.
Okay.
Yeah, so through what we get through today. And I'll send out something for you all in terms of like something to review for the exam, which would be a week from today.
Thank you.
Okay, so last time, the main takeaway from last time is that if we look at the derivative of any function and figure out where it changes, where the derivative changes from positive to negative, we have a local maximum there, as long as the C, the place we're looking, is a critical number or critical point. So positive to negative means we have a local max, negative to positive means we have a local min. So now I'm going to introduce a new concept. Okay, everything we did last class had to do with a function increasing or decreasing. We have this new idea now today of this thing called concavity, or the concavity of a function. So concavity has to do with the shape of the graph, but it has nothing to do whether or not a graph is going up or down. It has to do with whether or not the graph has a downward curve to it, downward curve, or an upward curve. So let me show you first visually what I mean. So here's a graph of some function, and what I want you to notice is that as you go from left to right on this, I'm going to highlight this section of the graph here in red. Notice that anywhere on that red section of the graph, it's shaped like a frown. Okay, not like a smile, but like a frown. Do y'all see that? This red part looks like it's part of a frowny face. Mm-hmm. Okay. And then between this point and this point, this green part looks kind of more like a smile, like part of a smile, right? Maybe just like half of a smile. And then it switches here at this point. It switches at this point, and now it becomes a frown again until you get to about right here, where you switch again and it starts to look like a smile again. So we have frown, turns into smile, turns into frown, turns into smile. Do y'all see that?
Yes, sir.
Do you see that it has nothing to do with increasing and decreasing? Because like on this red part, on the left side over here, we're increasing, right? The function is going up, and then it decreases. That has nothing to do with the frowning and smiling idea. So the frowning and smiling is just kind of this downward or upward shape that we have. So that is referred to as the concavity of the function.
What determines, like in the first switch, what determines where that switch is? Because couldn't it be higher up still or lower down and it'd still be, the same?
Well, yeah, so there is a point here which it switches, and the question is, how do we determine where it is? Because it looks like maybe it could have happened a little higher up or a little lower down, but there is some special point where it switches, and I'll tell you exactly how we determine it. So this is it right here. If you look at the second derivative of a function, not the first derivative, you look at the second derivative, anywhere where the second derivative is positive, you're going to be what's called concave up or concave upward. Now, concave upward means smile. Okay, that means it looks like a smile. I always think about it this way. Second derivative positive, positive people like to smile, right? Concave up. Second derivative negative, negative people like to frown, concave down. All right.
Can you say like convex versus concave, or
It's concave. It's
There's-
concave. Yeah.
there's no
Convex is
convex?
something different.
Okay, thank you.
Now, so anywhere where the second derivative is positive, we're concave up. Anywhere where the second derivative is negative, we're concave down. And to answer Austin's question, the point where it would switch would be where the second derivative is 0, or perhaps undefined. So if you go back to what we did last class, okay? Last class, what we did is we tried to figure out where a function was going up and down, increasing and decreasing. So what we did was we found the critical numbers by taking the first derivative, setting equal to 0, figuring out where it's undefined. We draw a number line and we would test these points, right? And we'd figure out where the function is going up and down. That's what last class was about. Today, we're going to do the exact same thing, but with the second derivative. We're going to figure out where's the second derivative, positive and negative. That'll basically help us determine where the function's concave up and down. And then we'll have these points where it switches. And anywhere where it switches is called an inflection point. Okay, so a point on the curve is called an inflection point of the function. If the second derivative changes signs at that point. So if it goes from positive to negative or negative to positive, we have inflection points. All right, so I think the best way to do this is just to get into an example and see how it all plays out. So here's your first example. I'm going to give you a function f of x equals, we're going to start with an easy one, 36x plus 3x squared minus 2x cubed. And here's what I'd like for us to do. Part A, find where that function f is increasing, find where it's decreasing, find the local maxes, and find the local minimums. That's all what we did last class, okay? Part B is I want us to find where the function f is concave up. So to show you concave up, I'm going to draw a little U like that. That means I want to know where is it concave up. Okay, I also want to know where's the function concave down. That means that's the way I'll draw it if I want to know where it's concave down. And then I want us to find the inflection points. We may or may not have inflection points, but we're going to just try and find them if we do. All right, y'all ready? Okay, so to do this problem, we're going to need to look at both the first derivative and the second derivative. So let's just take some time to get both derivatives. Okay, first derivative of this function should be no problem for everyone in here. All right, that's our first derivative. Our second derivative is just the derivative of that, which would give us 6 minus 12x. So I've got those ready to go, and now I'm going to start doing the different parts of the problem. Okay, so part A. To figure out where the function is going up and down, where I have local max and mins, I'm going to find the critical numbers. So I'm going to take the first derivative, set it equal to 0. And I'm also going to look at the first derivative and figure out where it does not exist. Those are the two things I need to figure out. So I take my first derivative, 36 plus 6x minus 6x squared. I set it equal to 0. And let me see, I can clean this up a little bit. I can divide everything by 6 and still have a quadratic equation. I can also move everything to the right side to make my x squared positive. I'm just doing this because it'll be easier for me to factor. Just moved everything to the right. And now we got kind of lucky because it does factor. If it didn't factor, we'd have to use a quadratic formula. But it does factor x minus 3x plus 2. And so we have two solutions, 3 and negative 2.
Question.
Yes.
Could I have factors at the very beginning
Yes.
when we first started? Like, would it have directly, so like I guess, but like with the original equation, could we factor it there first or
Here?
yeah, like
Yeah.
yeah. I could factor
Yeah,
it
you could
right
have done
and-
it there. Yep.
Okay.
You get the same
Okay.
answers. You get the same answers.
Okay then, yeah, because I was just like, I want to take it apart already. Okay,
Yeah.
thanks.
Okay, now what about the derivative not existing? Does this ever happen?
Not in this one.
No, right? Because it's
No,
a
it's
polynomial.
polynomial.
So, yeah, we're not worried about that then. Okay, so now continuing again from what we learned last class, we would now draw a number line. We would draw the two critical numbers, negative 2 and 3. That would split our interval up into 3 regions, and we pick test points. So I'm going to pick negative 3. I'm going to pick 0 because 0 is a nice number in there. I'm going to pick 4. And where do those get plugged in?
Derivative.
The derivative
Derivative, right? Okay, I did what? like
right now
12
it's just the
exclamation
first one?
points? I'm sorry?
Oh, I said right now it's just the first derivative. We're not plugging in for the second one, or is that
That's
the
right.
next? Okay.
Yeah, we are just doing what we did last class. So everything that we're focusing now on is everything to do with the first derivative. So I'm going to plug negative 3 into the first derivative, 0 into the first derivative, and 4. And all I care about is whether or not I get a positive or negative answer, right? That's all I care about. So we're plugging into this guy right here. I'll just bring it down here so we can see it. So this right here, if we plug in negative 3 into this, here's the way I would do it. If it were me doing the problem, I would actually factor that 6 out. And I would actually factor this. Well, you know what? That's going to be a little hard. Let's pull a negative 6 out instead. Let me do that. I'm going to pull negative 6 out. And that'll give me negative 6 minus 6x, sorry, negative 1. Negative 6 minus x plus x squared. I pulled a negative 6 out because I really want a positive in front of the x squared. I'm going to switch the order around. God dang it, Robert. And then okay, you don't have to do this step, okay? You don't have to do this. You could just plug negative 3 into this, plug 0 into this, plug 4 into this, and see what you get. So if I plug in negative 3, let's see what would happen. I would have a negative 6, then negative 3 minus 3 is negative 6 again, and then negative 3 plus 2 would give me negative 1. And what I'm most concerned about here, what's most important to me here, is that this is a negative number. I don't care what the number is. 2 negatives or 3 negatives multiplied together give me negative. What does that tell me?
Going down.
The graph drops.
Okay, the graph of f, right? What I can say is over here, the graph of f is going down. That's what I can determine. Because when I plugged in negative 3, I got a negative answer. So the derivative over here is negative, which means the original function is going down. Now, when we plug in 0, you should get a positive number. I'm not going to go through the work. And that means that the graph here should be going up. And if I plug in 4, work it out here, you'll get negative again. So it goes down. Now, students always ask me, like, see how it switched and went down, up, down? Students will always ask me, can I just find the first one and then just know that the others are just going to keep switching? And the answer is no, it doesn't always switch. In fact, we did a problem last class. Here's an example we did last class where it went down, up, up, down. So see, it didn't switch. So you have to find them all. You have to check. All right, unfortunately. Whoa. Come on, come on. All right, so this was negative here, so it goes down. All right, so let's answer part A. So for part A, where is the function going up? Well, that happens right there on that yellow part, right?
-2 to 3.
-2 to 3. So I'm just going to say on the interval -2 to 3. Now it's going down on the green part, here to here, and then here out.
-infinity to -2 union 3 to infinity.
Yep, exactly. Everyone understand that? I mean, we did this
Yes,
last
sir.
time. Okay. All right, how about local max? Do we have a local max?
Yeah. Oh.
Where is it at?
It's the points that you gave us, a -2 and 3. If you're talking about the x, of course.
I want to know, yeah, what's the x coordinate where the maximum, local maximum occurs?
3.
Just 3. Just 3, right? Because at 3, it goes, the derivative goes positive to negative, so it goes, the function goes up and then back down here. So I must have a local max at x equals 3. That's where we have a local max. Now, I always like to get it as a point. So as a point, we can plug that value into the original function, the original one way up here, and we'll get an answer. I'll just do it on my calculator real quick.
I have a question. Do we have to get a
If you are
point?
calling about making a payment, electronic.
Do you what? Do you what? What?
She's asking if we have to get the point or if we could leave it as just the x equals.
I think you should get used to getting the point. So yeah, get the point. I'm getting 81. So written as a point, I have a local maximum at 381. Now, in terms of a local minimum, well, that happens here at -2 because we go down and up. So we have that at x equals -2. So if I plug -2 into the original function, we get, let's see. I'm getting -44. I'll double check it in a minute when we look at the graph. So -2, -44 looks, this point right here is where we have a local minimum. Not a global minimum, right? Not an absolute minimum. This is a local minimum. The only way we can find absolutes is if we're on a closed interval. That was the first section from this chapter. Okay, are we good? Everything we've just done, all of that is part A, and everything we did here had to do with the first derivative. Was there a question?
I have a quick question.
Yes.
When you had the first derivative, and you're setting it equal to 0, did you factor out the -6, or did you just like leave that out?
Well,
Because I was
because,
kind of confused how you got.
yeah, because I have an equation, only because I have an equation, I can divide everything by 6. And that gives me 6, and then this gives me an x, and this gives me a -x², and then 0 divided by 6 is still 0.
Okay.
That, now, it's only because I had an
Okay, that
equation,
makes
it's
more
because I set it equal to 0.
Okay.
I have a question. I don't know if it's really a dumb one or not, but so if we just took 3 and -2, would it be safe to say oh shoot, how do I want to word this? If we just plugged in 3 and -2 into the function, could we just assume, or with whatever points that we get, could we assume that that is going to be our local max or min, or should we go through this whole process?
You have to go through the process. Here's why. Just because, what do you mean? After you have all this, you mean, or just?
Kind of skipping over that and just plugging in 3 and -2 into the original function.
Okay, yeah, no, you can't, because you don't, all you know is that the derivative is 0 here, right? That's all you know. Like here at 3 and -2, the derivative is 0. So that means that your graph, just to show you an example that wouldn't work. What if I drew this graph for you? Okay, so I tried to draw the best I could. Here, the slope of the tangent line is 0 because it flattens out there. Do you see that?
Mhm.
And do you see over here the same thing? The slope of the tangent line there is 0. So I've just given you an example of a function where at -2 and 3, the derivative is 0. However, this graph, there is no local max or min. Do you see that? I don't know, like, this is not enough information for me to tell whether or not it's a local max or min is happening there. I have to see the change in the derivative. I need to see that change, that going down to up, or I need to see the up to down.
Okay.
Does it make sense what I'm saying?
Yes, sir.
Okay, good. Yeah, trust me, if there were an easier, quicker way, I'd give it to you. I mean, trust me, I would, because we're trying to find the shortest path to the answer. Unfortunately, it requires this amount of work, and we're only halfway through the problem. So, all right, now we want to look at part B. I want to talk about the where it's concave up and concave down and inflection points. So now what I'm going to do is everything I just did, but with the second derivative. Okay, so this is the new stuff for today. So for part B, we want to take a look at the second derivative, and we want to know where is the second derivative equal to 0, and I want to know where the second derivative doesn't exist. Let me take care of the easy part first. It's never not going to exist because the second derivative is a polynomial function, right? It's a line, actually. So there's nothing I can plug in that's going to cause a problem. Now, on the first part, setting equal to 0, well, luckily for us, this is an easy equation to solve, relatively easy. Just move the 12x to the other side, divide both sides by 12, reduce the fraction, you get x is a half. Now, same thing like what Natalie just asked a second ago, is this enough for me to know anything? And the answer is no. I need to now know what's happening near that point. So I put 1/2 on a number line. And then I picked 2 new test points. How about 0 and 1? Those look like good ones. And where do these get plugged into?
The second derivative.
Second derivative, because I'm trying to figure out if I'm smiling or frowning, right? So if I go and I take the second derivative and I plug in 0, I need to see what I get. Second derivative, plug in 1, I need to see what I get. And luckily for us, the second derivative is pretty nice. So it should be easy for us to figure out what happens when we plug these in. So let's see, if we plug in 0 into this, we just get 6. And that's a positive number. Y'all agree?
Yeah.
Yeah. So what does the second derivative being positive tell me about the shape of the graph?
It's enough.
It's gonna smile.
It's going to smile. It's going to be concave up. So that means over here near where we're testing at 0, I know that the original function is going to be something concave up looking. Now, when I plug in 1, I go 6 minus 12 times 1, that's 6 minus 12. That's going to be a negative number. And that means that over here, my second derivative is negative, which means that the original function must look like a frown or a concave down over here.
A pessimistic view.
And then does that make a 1/2 our inflection point?
And that makes 1/2 the inflection point. So we can now answer the question. So I'm answering the question right here. Where is the function concave up? Let's see. Well, it's concave up over here, isn't it? The whole way from here to the left. So I'll write negative infinity to 1/2. Where is it concave down? From 1/2 to positive infinity. That's this way forever. And then where do I have inflection points? I'm just going to put IP for inflection points. Do I have any?
X is 1/2.
X is 1/2.
Right.
Now, I would like to plug that into the original function and figure out what I get. Now, I would definitely use a calculator for this. I'm going to go ahead and do that right now. I get 18.5. So as a point, it's the point 1/2, 18.5. I've answered all the questions here. And come back to this right here. I'm going to put my answer here because I want to look at all this. So here's what we have. The graph of this function should be going up between -2 and 3. It should be going down to the left of -2 and to the right of 3. It should have a local maximum at the point 381. Should have a local minimum at -2, -44. It should be concave up to the left of 1/2. It should be concave down to the right of 1/2, and it should have an inflection point at 1/2, 18.5. Here's the graph. Okay, so let's look. What's that point right there? 381. Do y'all see that at 381 we have a local max?
Yes.
You see down here at -2, -44 we have a local min? Do you all agree that we are decreasing? Let me do it in red. Do you agree that we are decreasing until we get here? And then we start increasing. That's first derivative, still working first derivative, then decrease. So to the left of -2, we're decreasing. To the right of 3, we're decreasing. Between -2 and 3, we are increasing. That's what we had, right? That's all the information we had. Now, what about inflection? So we said to the left of 1/2. Where's 1/2? It's hard to see here, but here's 1/2. This is 1. So we go up to our graph here. If we look to the left of 1/2, that should all look like a smile. It does, right? If we look to the right of 1/2, it should all look like a frown, which it does. And this point right here is where we have the inflection.
At the inflection point, is it the same equal distance between the local min and local max?
It doesn't have to be.
Okay.
It doesn't have to be. It can be, but it doesn't always have to be.
Is the only time we'll have like no inflection point whenever it's just like a concave up or a concave down? Only.
Yeah, like a parabola. Just if you were to just think about a parabola, right? If you just had a graph of parabola, a standard parabola is always concave up. And that means it's never concave down, which means you never have an inflection point, right?
So you would need to have an odd number power for the polynomial. Yeah, I can't pronounce it right now.
For a polynomial, do you need an odd power to have what?
What we have here, because you said to have an inflection point, it needs to have a turn in it.
Well, I didn't say we have to have a turn in it. I said that you have to have a change in concavity. You have to go from concave up to concave down. You don't have to have a turn to have that happen. I'll give you, just let me clear this out of here. Let me give you an example. How about just x cubed? There we go. Look at that graph right there. That's x cubed. This curve does not have like a turn. I think, Benjamin, you were asking, right?
Yes.
This doesn't have a turn. I think by turn you meant like something like that. Like that's a turn. Is that what you're referring to? Okay. So this one in red does not have a turn, but it does have an inflection point, because here's your inflection point. To the left of it, it looks like a frown, right? And to the right of it, it looks like a smile. And so you do have an inflection point without a turn.
Okay.
So look, the easiest way to figure out whether or not your graph has inflection points is you have to take the second derivative. You have to set it equal to 0. You have to figure out where it doesn't exist. You have to draw a number line. You have to test the points. You have to look for a change. That's what you have to do. So it's a long drawn out process, isn't it? I mean, this is a long drawn out process here. All right, y'all ready to do a new example?
Yeah. Woo.
There we go. Let's go back to last class. I'm going to take this right here. We're gonna do this problem. Let me see if I can get to today. Where are we? Here, I'm gonna copy it over to today. Okay, let's take this example that we had worked out. This is, I believe, the last example we did in class. Yeah, this was the last example that we worked out in class yesterday, or 2 days ago. I gave you this weird function with fractional exponents, and I asked you to find where it's increasing and decreasing, and we worked on this together. Well, I think I had you work on it, and then we came together and worked on it. And here's what we found, okay? This is what we found. So this should all be in your notes already. Now what I'd like to do is ask you where this function is concave up, where it's concave down, and whether or not it has any inflection points, okay? So what are we going to need to do?
Take the derivative of the first derivative.
Yeah, we're going to need a derivative of the derivative again, right? Because we have here, this was our derivative from last class. It was right here. I put it in a box. I'm going to go ahead and cheat and take that. And I'm going to work on this on another page. So I'm adding to this a new part to this. I'll call it part B, where I want to find where this function is concave up, find where it's concave down, and then find any inflection points. So I take my derivative, here's my first derivative. Let me erase some stuff here. This was f prime of x. And so now I need the derivative of that derivative. So I need a second derivative, which means I'm going to have to break out the quotient rule. Or do I have to, I guess?
Oh, I'm trying to see that too.
I don't have to, but I'm going to. I'm going to break out the quotient rule. So I take the derivative of the top. What's the derivative of the top?
And
Negative 10.
Negative 10 times the bottom minus, now the derivative of the bottom, be careful here.
1.
Yeah, so the 1/3 hits the 3, becomes a 1. So x to what power?
Negative 2/3.
Negative 2/3.
Negative 2/3, good. That's the derivative of the bottom times the top, 10 minus 10x, all over the bottom squared. Now I realize that looks bad, and we have to set it equal to 0, right? So this means it's algebra time, right? We have to do some algebra. Let's clean things up a little bit. So let me see, do you agree with this? This is negative 30 x to the 1/3 minus, see if you can follow this, 10 minus 10x over x to the 2/3, all of this over 9 x to the 2/3. Okay, so all I did here was multiplied those two together, got negative 30, subtracted This x to the negative 2/3, I dropped it down as a fraction and put it underneath this. So that's this. Then the bottom, I squared the 3, and then I squared this. So when I squared that, I did x to the 1/3 squared, and that's when you multiply those two together. 2 times 1/3 is 2/3. Anybody have any idea what I'm going to do now?
Conjugate?
Can you factor out the exponents?
We have a
Anything
complex
like that?
fraction, right? We
Oh,
have
a complex
fractions within fractions. What have I always done when I've had fractions within fractions?
You make the numerator an equal denominator.
Yes. I agree with the hand movement.
That's the hand motion, yeah. You get a common
Yeah.
denominator in the numerator. I try to put those two together. Okay, so what I mean is I want to rewrite this. I'm just going to save myself some time. I'm going to rewrite that as negative 30 x to the 1/3 over 1. So you have two fractions here. And I'm going to try and combine them together. Which means I have to introduce what here? What do I have to introduce on the first fraction to get the same denominator here?
X.
X
to the
X to the
2/3.
2/3.
The 2/3. Do it on the bottom and the top. So we have, let's see, what happens? What's x to the 1/3 times x to the 2/3?
You get a whole X.
3/3.
3/3, so that's x to
That
the
gives me
first
1.
power.
Yeah.
So negative 30x, that's nice. And then I have, that's going to be this numerator, and then I have minus. And then this numerator, I need to put it in parentheses. All over the common denominator, x to the 2/3. But all of that is over 9x to the 2/3. So when I started this class, very early in the class, I told you all, you know, algebra is just one of those things that is a weakness for a lot of Cal students. And now we're seeing like you're truly going to be tested in your algebra now. You know, you've made it up to this point. A lot of times when we were doing derivatives, we did raw derivatives, but I always said at some point we're going to have to work with this stuff. So I understand that this is a little bit, might be a little tough for some of you. You just need to practice. You need to do the homework, you need to redo it, you need to see how the algebra works. Because technically it's just algebra, right? That's all it is, it's algebra.
Yes.
Okay, so now I'm going to do something here. I'm going to take a fraction. I have a fraction over a fraction. And so I'm going to flip and put it up here like this. Get rid of it there. And I'm going to distribute the minus through. And I'm getting close to a nice answer here. Negative 30x minus 10 plus 10x all over. When I multiply those two together, you add the exponents, you get 9x to the 4/3. One more step. Negative 20x minus 10 over 9x to the 4/3. And I think that's about as pretty as it's going to get right there. I get to a point where I'm looking at it going, okay, I'm okay setting that equal to 0 now. I'm okay looking at that and figuring out where it's undefined. So now that's the step I need now. Where is the second derivative equal to 0? Where is the second derivative not exist? Okay, so how do we figure out where it's equal to 0? What am I going to do with this?
Equal to
The
0.
denominator. Yeah, putting it equal to 0.
Just what? The what?
At the top equals to 0.
Top to 0. Okay, top to 0. Numerator to 0, and that's all I have to worry about. All right, just be careful here. You're just going to move things around. This is a linear equation. Everyone here should be able to solve this. Negative 1/2. Now, how about where it doesn't exist?
Set the bottom to 0.
Yeah, figure out what makes the bottom bad. And there is a problem here, right? At 0?
Yes.
Yes.
Okay, and is 0 in the domain of the original function? We got to go back and look at the original function. Here was the original function. So I can plug 0 in here and there's no problem. So I'm going to need to include that as my critical number for the second derivative. So x is 0 is my other one. So I have two numbers that are going to go onto the number line.
Could I have factored out a -10 right there?
You would have got the
Like-
same answer.
Right, and I would have already had an x minus 0, or the x equals 0 without having to look at anything, right? I mean, of course, we're going to check, but
If you would have factored out a -10 here,
yeah, because don't you set that equal to like something? I don't remember. Like that.
yeah, but
I
if
think
you
it's like
pull a -10
0.
out here, you would have that, right?
Uh-huh.
And you set that to 0, you get that. But -10, you do not set equal to 0. That doesn't give you 0. -10 can't be 0. I think what you were saying is that this would give you the 0 from here. No?
Mm-hmm.
Yeah, that's not 0. So you just ignore that.
Got it.
Yeah, the 0 would only come from the denominator part. Now, had you factored out a -10x, like let's say this would have been like x squared minus 10x, then you would have had x is 0 too.
Okay, thank you.
Wait, why this is 0 though?
Because the second derivative, which is this, right?
Right.
If I try and plug 0 in right here, I'm going to get division by 0, right?
Right. So
And division by 0 would make the second derivative not exist because you can't divide by 0.
so how did you figure out like 0 is the only one, not the others? Like
What
how do you
others?
know just only 0? Like how do you figure out that number? Okay, just 0 is not gonna work.
Well, you just have to look at it. You just have to say, okay, look at the denominator, right? What's
Mhm.
the only number you could plug in here that would cause division by 0,
Okay.
right? So try any other number. If you do any other number, you're going to get some number here times 9. You're going to have a number. You're not going to have 0. The only way to get 0 is if x is 0.
Got it. Thank you.
Got it? So it's just an inspection thing, a visual inspection. All right, what's next?
Fine. Quick
You would
Check.
pick points outside or inside the what you have on there.
Yeah, so some test points, right?
Yeah.
So something over here, here, and here. So who wants to give me something over here?
-1,
Okay, that'll work. How about in here?
-1/4, -1/4,
Okay, -1/4, 1/4. And then here,
1.
1. Okay. And where are these going?
Dude,
The second derivative.
This one right here. Yep, they're going into that. So I need f double prime of -1. I need f double prime of -1/4. I need f double prime of 1. And again, all you care about is whether or not you're getting a positive or a negative out. That's all that matters. So we're going to plug -1 in. Well, you know what? Before I do it, I want everyone to look at the denominator real quick. 9x to the 4/3. I want to make sure everyone understands that that means this. X to the 4/3 means you're taking the cube root of x and then you're raising it to the 4th power.
So that'll make it positive if it's a negative then.
Yeah, so the reason I'm saying that is because no matter what happens, no matter what you ever plug in, the denominator in this problem is positive. Okay, always. So really all we care about is what's happening in the numerator. So if I plug in -1 for x, I get -20 times -1, which is 20. Take away 10, I have positive. So this should be positive here.
Mm,
What about -1/4? What's -20 times -1/4?
5.
Positive 5.
Yes.
Take away 10.
-5.
Negative.
So negative.
And if you plug in 1, -20, take away 10, -30. So you have negative. Ooh, it didn't switch. You see that? It didn't switch. All right, so here's what we know. We know that over here near -1, the original function must be concave up, smiling because it's positive. And then the rest of the time, the function is not happy.
So does that mean there's not an inflection point at 0?
That is correct. We do not have an inflection point at 0.
Okay.
So let's now summarize. Our function is concave up from -infinity to -1/2. It's concave down. So concave up was this part. Concave down is going to be here and here. So we'll just put it all together. So that's going to be from -1/2 to infinity. Inflection point. Do I have an inflection point?
-1/2.
Oh,
-1/2. That's the only place, right?
Yeah.
-1/2.
my bad.
And so if you take that and plug it into the original function, we're going to get some number. I'm not going to do it on I could get my calculator out and do it into the original function. I'm just going to go show you the graph. Okay. Any questions before I go look at the graph?
Is there any like application problems we're going to be doing with this?
Oh yeah.
Okay.
Oh yeah. Yeah, we're all leading up to word problems here.
Oh no.
Yeah. Okay, so when we draw this graph, back from last class, it should be increasing from 0 to 1 and decreasing everywhere else. We have a local max at 1, 3, a local min at 0, 0. Then we should have concave up to the left of a half, concave, to the left of -1/2, and concave down to the right. And we should have an inflection at -1/2. Here it comes. So let's talk about what we determined last class. It's decreasing, 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 decreasing until we get to 0. Then it increases. And then here it looks like at 1, 0. Did we not 1, 0, at 1, where was it? 1, go back. At 1, 3, we have a local max. I need to change my grid here. Hold on. Let me make this -10, 10. There we go. That's a little bit easier to look at. Clear that out. Okay, so all of this is where we're decreasing, right? Decreasing, and then we switch to increasing, increasing. We get to a local max. Oh yeah, by the way, this was a local min. That's a local max. And then we start decreasing again, decrease, 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 right? That matches what we got from last class. What we just learned. Go
I
ahead.
thought we didn't have an inflection point at 0.
What's that?
I thought we didn't have an inflection point at 0.
I thought we don't have an inflection point at 0.
Okay.
Yeah, let's talk about why we don't. Okay, so that's all first derivative information. Now, what we just learned today with this problem is that we should have an inflection point at 1/2, right? So 1/2, which is here. Wait, was it 1/2? -1/2.
-1/2.
-1/2, sorry. Let me zoom in a little bit more here. There we go. At -1/2, which is right here, we have an inflection point. Ooh, that's hard to see. It's hard to see that that's an inflection point. We should have what did we say to the left? It's concave what? Up. So the graph should be looking like concave up over here. And then it should be concave down. Do y'all agree this piece looks a little bit like it's concave down, especially right here? You can see the curve in it.
Barely.
Yes? Barely. And then over here, see, this is still concave down, right? All of that's concave down. See, the reason this is not an inflection point at 0 is because we don't switch concavity. We don't go concave down to concave up. We go concave down to concave down. Inflection points are where you have a switch. I'm not sure who said that. I think it was Benjamin, right? You asked?
Yeah.
Yeah, do you see why it's not an inflection point at 0?
Yeah, it was just a little bit tricky, I guess.
It is tricky. And so the shape of the graph, even though it looks like there's something happening there with inflection, there's not. Now, I don't think I've convinced you here that this is an inflection point. And that's the strength or power of the calculus, is that the graph may not suggest that that's an inflection point, but it is. What I'm going to have to do to maybe convince you is change my y-axis a little bit. Maybe if I change that, it'll make it a little more obvious. No, that doesn't help.
Sir, just to be like certain, an inflection point is when the graph changes, like how it curves partially way through, right?
Yeah, it's smile to frown or frown to smile.
Okay.
Think about it this way. At the end of the day, there's only two possibilities you can have with an inflection point. You can have a smile that turns into a frown, or you could have a frown that turns into a smile. Those are the only possibilities you can have when it comes to inflection points. Do y'all see that? This is concave up, switching to concave down. So it's kind of like where this smile, the corner of the smile meets the frown right there. And then this one is concave down, meeting up with concave up right there. The frown becomes the smile. It's a weird transition point. Okay. Now you might wonder what's the importance of an inflection point? Like, why is an inflection point an important thing, right? It seem reasonable? Like, what's the point? I think you can agree with me that the first derivative, doing this thing with the first derivative where we do this table and we figure out where it's down, up, I think you would agree with me that that's valuable because it shows us local mins and local maxes, right? And it might be useful for us to know where these lowest and highest points on a graph are. But inflection points, that may not seem to be important. So let me show you in real life, like where an inflection point's important. Oh, you know what? I took a screenshot of something the other day. Hold on. I was reading something and I took a screenshot because they used the word inflection point. And I was like, I'm going to use this in class. Hold on. Where is it? Just give me one more second here. Here we go. So the Federal Reserve chair, the chairman of the Federal Reserve, his name is Jerome Powell. He's an economist, you know, for the United States. He said that our economy, and this was a while back, this was back on April 12th. He said that the US economy is at an inflection point and that growth and job creation is poised to accelerate. Okay, so I saw that, and I don't see inflection point used very often. I read the news, or I read things in the news, or I watch TV, and I always hear people always talk about exponential growth. They always say that. So that's like when I hear math, but I never hear inflection point. So he said that our economy is growing and we've reached an inflection point, and we should expect job growth and creation to accelerate. So let me show you what that looks like. So let's say that this is time, and let's say this is number of jobs, just to keep it simple. Okay, what the federal chairman was saying is that right now jobs are being created, all right? Like job growth is increasing, right? So job growth is increasing, but No, the other way around. Job growth is increasing, but we've reached an inflection point. So what's going to happen now? Do you see that to the left, we are concave down, right? We've reached an inflection point, which means now we're going to keep growing, but concave up. And so if you look at the slope of the tangent line here, anywhere over here, do you see that the slope of the tangent line is positive? So we're growing, right? To the right of that inflection, all these tangent lines are steeper because we're on a smile instead of on a frown. So he's saying, look, we've got job growth and we've reached an inflection point where we can expect, in his words, we are poised to accelerate, which means that the slopes of the tangent lines are going to continue to go up steeper. Does that make sense? Now, you can also look at this in a more negative light. Like, let's say that you have a company and here's time and here's your, let's say, profit. And let's say you're looking at your profit over time for your company and you see this. Growth, profits going up, profits going up, profits going up. You hit this point and now you go like this. So at this point, are you still getting profit? Is profit still growing? I mean,
Yes.
profit's going up this whole time, right? But something happened here. See, to the left of this point, you've got pretty steep tangent lines, don't you? Those are pretty steep. But as you're moving to the right, because you're concave down over here, do you see that these are not as steep? So this is like the reverse of what the economist just said. This is like, okay, I have this company, we're making money, we're making good money, we're making good money. We hire Robert. This is when we hired Robert, and we put him in charge of maintaining our I don't know, all the boxes and shit in the back of the warehouse, right? They put me in charge, and all of a sudden things start going downhill a little bit, right? Not literally downhill. We're still making money, but not as fast as we were making money. It must be, Robert. You know, but that's what a business would look for. They look for, where are these points, these inflection points where, yeah, things are still good, but not as good as they were. What changed, right? What made that inflection point happen? All right, I hope that makes sense. Okay.
It does.
You're ready for another example? We looked at the graph, right? Oh, we looked at the graph, right? Yeah, okay, so I have another one for you. F of x equals natural log of x to the 4th plus 27. I want to do this one because this function seems to like come out of nowhere. So first step, I'm going to give you 2 or 3 minutes. Get me the first 2 derivatives. We're going to need them, right? The steps, the instructions on this problem are going to be basically find where it's going up, where it's going down, local max, local min, concave up, concave down, inflection points. So take a minute or 2 to get the first 2 derivatives. I'm putting these derivatives up here so you can check to see if you're doing it right, but I've got to run back through this to make sure I'm doing it right. So hold on. Does that all look good to you all? What I did there?
Yeah.
Yeah.
Pointed out.
Looks about
Okay,
right.
so I think this is it. So we've got derivative natural log of something is 1 over it times the derivative of what's inside. That's chain rule. Slide that on top. There's my first derivative. Second derivative, I got to run quotient rule. So derivative of top times bottom minus derivative of the bottom times top over the bottom square. Okay, clean this up. Distribute. 12x to the 6th plus 27 times 12, right? 324 x squared minus 16 x to the 6th all over x to the 4th plus 27 squared, which is negative 4x to the 6th plus 324x squared over x to the 4th plus 27 squared.
Where does the oh never mind. Never mind.
So distribute, combine like terms. These two are like terms, so I put those together, put it out front. And I think that's okay. I think I'm going to say this is my first derivative, right there. And then here's my second derivative, right there. Questions?
Rando question. So earlier with the first derivative, could we have subtracted the exponents or no?
What do you mean?
Like the 4x to the 3rd and then the minus x to the 4th, wouldn't that just get like, you know what I mean? Like,
Oh
because
yeah,
it's
no, because
division.
you have two terms on the bottom, one on the top. So you can't do this over this.
Okay then, because it's something. Got it. Found it.
If it were multiplication, you could, but it's addition.
Okay then.
I expanded the bottom of the second derivative to be like x to the 6th plus 729. Did you want us to keep it?
Wait, say again?
I
Oh, you foiled that out? Is that what you're saying?
well, yeah.
Oh, you squared each one.
Yes.
You would have to foil it. You would have to
Oh.
actually do like 2 parentheses and distribute. I'm not going to do that. I don't think we'll need to do that in the problem.
Okay.
Yeah, we just need to figure out if it's positive or negative once you plug the numbers in, right?
Yeah, now we get down to business, right? We've got the two derivatives. Let's get down to business. So let's talk about where the function's going up, where it's going down. Let's talk about local max, local min. Okay, to do that, we're going to take our first derivative. We're going to figure out where it's 0. We're going to take our first derivative and we're going to figure out where it doesn't exist. Okay, first derivative equal to 0. Here's my first derivative. Set it equal to 0. Easy money, right? 4x cubed. That's all you have to do. Just the top. Divide both sides by 4. Look, the answer is 0. The only thing you can plug in there and get 0 is 0 itself. Now, where does it not exist? So this is the question we were asking earlier. When would this be undefined? When would that yellow part be 0?
When it equals negative 27.
Well, this would have to be equal to negative 27, wouldn't it? For that to be 0. But any number to the 4th power can never be negative.
That's true, yeah.
Right? So no matter what number you ever plug in here, we raise it to the 4th power and add 27, it's got to be a positive number, right?
Yep.
Can't be 0. which means that this doesn't ever happen. I never get division by 0.
So could we say that if the denominator is a polynomial by
I
itself?
I can barely hear you, whoever's asking. Go ahead, Elise.
Can you hear me a little better now?
Yeah, that's better.
So can we say that like when the denominator is a polynomial by itself, then it will never be equal to 0 and it'll always exist, the entire.
Well, no, because if this was minus 27, then it would have an answer. Because what we're using here is the fact that anything to the 4th power would be, at the worst, it would be a 0. But if, you know, like if you plug in 0 here, you get 0, but then you add 27, that's not 0. If you plug in any other number, raise it to the 4th power, it's positive. Then you add 27, that's still never going to be 0. Do you understand, Elise? If that had been a minus, then we would have trouble.
Yeah, I hadn't thought of that.
Okay, but you understand now? Okay. So now we are critical number 0. Pick a point, -1, 1. Plug these into what?
The first.
First derivative. Okay, plug them in into here. So when I plug them in here, when I plug in -1, I get a negative, because I cube a -1, I get -1. So -4 on top. And then what can everyone tell me about the bottom, no matter what?
It's always going to be positive.
Always positive, right?
So
I get negative when I do that. So that means my original function goes down. And then when I plug in 1 into here, I get 4 on top, and we already know the bottom's positive, so we're going to get positive there. So the function goes up. I can answer the question now. The function goes up from 0 to infinity. The function goes down from -infinity to 0. Do I have any local maxes?
No.
Do I have a local max?
No.
No, none. I have no local max. Do I have a local minimum?
Yes.
Yes, at x equals 0. And so if I plug 0 into the original function, that means into here, up here, we just get natural log of 27, whatever that is. That's a number you can get on your calculator. First part's done. Now I need to figure out where the function is concave up, where the function is concave down, and where I might have any inflection points. So I take my second derivative and I set it equal to 0, and then I take my second derivative and figure out where it doesn't exist. Here's my second derivative. To set it equal to 0 means I just take the numerator and I set it to 0.
Plug in 0.
0 will work, right? Just by looking, 0 is a solution. The question is that the only one? So why don't we just try and do some factoring? Do you all agree I could pull a -4x squared out of both of those?
Most likely.
I think 4 goes into there. Yeah, it does.
Yeah.
It goes in there 81 times. I pulled a -4x squared out of both of those. Y'all following me?
Yeah.
Now, does anyone see what this is? Drum roll.
It factors out, not factors out, but
yeah.
The difference of squares.
Yeah, different.
Difference of squares.
Squares. Okay.
You have x to the 4th, so it's x squared plus 81, x squared minus 81. Oh, sorry, not 81, 9. I apologize. 9, 9.
I was like, what?
Yeah. Now, this isn't done either because x squared minus 9 is a difference of squares also. X squared plus 9, just make sure you understand, everyone, that does not factor. We do not have a formula in algebra that allows you to factor a sum of squares. You factor the difference of squares. That second one becomes x plus 3, x minus 3, but the other one does not factor. Over the real numbers, you can't factor that.
Mhm.
So that means that we try and set all of these equal to 0. So we get negative 4x squared equals 0, x squared plus 9 equals 0, x plus 3 equals 0, x minus 3 equals 0. And so we get one solution here of 0. This has no solution. Why?
You can't get it to equal 0.
Yeah, you can't get that to equal 0. X squared plus 9 can't be 0. You just check, move the 9 to the other side. X squared can't be negative 9. So no solution there. Negative 3 here and 3 here. Yes, that is your sad reality. Okay. You have 3 critical numbers, which means you're going to have 4 test points. 0, 3, negative 3. Test negative 4, test negative 2, test 2, test 4.
Is the equation always going to exist?
Is the what?
We didn't do f does not exist.
Oh shit, I forgot. My fault. I'm glad you reminded me. F double prime. Now it's not going to here because when you look at F double prime, right? You have to figure out what makes the bottom 0. And for the same exact argument that we had up here for this one, that can't be 0, so that squared can't be 0 either. So no here. But yes, you need to look at it. I forgot to look at it. I got ahead of myself there. Okay. Yes, your life is fun, isn't it? So you got to plug these in to here. Now, we can go and make this a little shorter if we want. We can realize that the numerator, we actually factored that to that, didn't we?
Yes.
Okay, and then what can you tell me about the denominator? No matter what I ever plug in, it's what?
Always positive.
Always positive. All we care about is the numerator, right? Just the numerator. So let's try and plug negative 4, not into this. Let's plug negative 4 into this. So what would happen if I go negative 4 right here? Negative 4 squared is positive 16, right? Let me grab this. So if I plug the negative 4 in here, I get negative 4 times 16. And then this right here, this doesn't matter. We know that's positive. We already said that it has to be. And then negative 4 here, square it, 16 minus 9. So we're going to get a negative number here, a positive number here, and a positive number here. Multiply all 3 of those together, and you get a negative number. What does that mean?
It's negative, like f double prime is negative 4 is.
So that means the original function is
down.
Negative.
okay, down.
Wrong.
Then we have to keep doing this for negative 2 now. So if I plug negative 2 into this, let's see what we would get. Negative 2 into that would give me a 4, and then I hit it with a negative 4 in front. The next number is positive no matter what. And then negative 2 squared is 4, take away 9, that's a negative number there. So I have negative, positive, negative, negative, positive, negative, which gives me
Concave up.
positive, right? So this means we're concave up. And if we plug in 2, +2, I'm not going to go through the work, but if you go through and do +2, you'll actually get concave up again. And if you plug in 4, you'll get concave down. I'm not showing those. Here's where we're concave up. Here's where we're concave down. So F is concave up on -3 to 3, concave down on -infinity to -3, union 3 to infinity. Inflections, do we have any?
Yeah,
Three.
Yeah.
-3 and 3, right? Not at 0 though. 0, we went from up to up, so there's no inflection there. We only have an inflection of -3 and +3. And then we could figure out what they are, right? We could plug those in and figure out. All right. I'm not sure how long that took us, but it took us a little bit, right? I mean, what happens if you mess up the first
Yeah.
derivative, right? What if you mess
Yes.
up the first derivative?
You're screwed.
I mean, the whole thing's off, right? The whole thing's wrong. So you got to be careful. All right, let's look at this graph.
So for oh my gosh, where we have the no solution, what goes on the graph at that point?
At where?
So where we have x equals 0, no solution, x equals -3, and yeah, what happens at that point, or do we just not worry about it at all?
Well, I'm not quite sure what you mean by that point.
I maybe not point, but like never mind. We could just look at the graph.
I think I know what you're talking about. The thing is, we know that at x equals -3, that'll make this whole thing 0, right? And if it's 3, it's all 0. And if it's 0, it's all 0. But this doesn't really give us a number to look at to say, oh, at this number, it's 0. In fact, this tells us there's no answer here. So there is no number that we need to look at. I think what you were trying to say is, okay, even though we didn't have a solution, what's happening there? But the question would be, where do you meet there? Like there is no there to look at.
Got you. Okay. Yeah.
Sense. Yeah.
No. That's exactly what I was asking. So yeah.
Okay. Yeah. Now, if we were living in the imaginary numbers, which we're not, then you could start talking about what's happening there. But we don't live in the imaginary numbers at all here. We stay away from it. Okay. It's like the candy jar you can't touch. Okay, so here we go. Picture. This is the graph. And I have long forgotten what we figured out. Okay. For the first derivative, it was to the left of 0, it's down, and to the right of 0, it's up. Does that look like what's happening here? To the left of 0. So over here, looks like the graph's going down here and going up here. I say that looks right. And then we determine that at -3, which is here, we have an inflection point. And at 3, we have another inflection point. We're concave down over here, concave down over here. And then in the middle, we are concave up, smile, smile. You see it? Frown, smile, smile, frown. Down, up. Local min, 2 inflections.
To find the inflections, you want to use math, right? Not just look at the graph.
Do you think you could look at this graph and tell me what the inflection points are?
Not if it's blatantly obvious, no.
Yeah, if it's not blatantly obvious, which I don't think it is here. So this begs the question, right? Calculus was developed before computers were developed. Calculus was developed before calculators were developed. Calculus students, people, humans were trying to get an idea of what functions looked like using calculus without the ability to just go to a website, type the function in and look at it, right? We have that ability, right? We live, it's 2021. We can go to a website, type in the function, have it graph it, shit. We just run our mouse over it and it'll tell us where the local min is, right? Like we have all this technology. So the question, you know, you should be asking yourself, like, how useful is this, right? Like, how useful is this process if we have this technology, right? And I would say that the usefulness is the fact that the technology is limiting in the fact that you can't nail down points exactly. You can try and you can guess, like if I go back to this function right here that we started class with. There's the polynomial we started class with, right? Like, it's hard to figure out where inflections are occurring. It's hard to figure out where these points are occurring just by looking at the graph. Now, if you're at this website, it does it for you, which is awesome. Okay. So, but with the calculus, we can get it exactly, right? There's no question about what the numbers are. So that's actually the question. I'm kind of putting a question in your mouth for you. It's why do we do all this if we have the technology, right? We should use the technology. So I'm actually going to agree with you in some sense, and I'm gonna do something this semester that I've never done. And it's really because we don't have time because of the snowstorm or whatever we had. The next section in this class is called curve sketching. And what we do in curve sketching is we put everything together that we've ever learned about sketching graphs. And we use all these different techniques to graph a function. So we go back to college algebra, we find the domain, we find the X and Y intercepts, we look for symmetry, we find any asymptotes that are occurring. Then we look at where it's increasing and decreasing. We bring in the calculus to figure out where it's going up and down. We find the local max and mins, right? Then we figure out where it's concave up and concave down. We're looking at the second derivative. Then we sketch the curve. Just forget this, make a table. Sketch the curve. That's what this section's all about, 4.4. Bring it all together. And these problems take forever to do, all right? Because you got to start from college algebra, right? So I think what I'm going to do is not do this section because we have the most important parts of this down now. We can do the calculus parts, okay? This part. The rest of it, yeah, we can just go to a graphing calculator, right? And we can just graph it. So I'm doing this only to save ourselves time, all right? That's really the only reason I'm doing it, to save ourselves some time and be able to get to some other information that we need to get to before the class ends. So you're welcome, because this is a bitch of a section, I'm telling you right now. Graphing functions by hand sucks, okay? It sucks terribly, all right?
Is this gonna hurt us in Cal 2?
No, it won't hurt
Except
you.
we already learned all of it since college algebra, so I imagine we all already know it.
Right.
Well, I mean, it's just the idea of putting it all together. That's the thing. In Cal 2, you do not have to go through and do a detailed sketch of a graph. You have to think about it this way. Curve sketching, this section, was developed and it's part of a curriculum in Cal 1 because there was a time, 30 years ago, where you could not just go graph a function easily. You had to have a mechanical way of doing it. Maybe 30 years is a push, 40 years, maybe, okay? I mean, there's been graphing calculators for a while, but they've evolved, right? They've evolved. I mean, y'all can't probably appreciate this right now because, I don't know, maybe you will appreciate this. So, you know, here's a different graphing, a different graphing website. So if I type in y equals x squared plus x minus 5. So I can graph a parabola real easily, right? This shouldn't blow your mind at all. I mean, this is just a parabola, big deal. But check this website, check out this website. I can do 3D graphing, okay? So there's that same parabola laying on the ground, okay? In 3-dimensional space. And then I can do something like, I don't know, I'll do a nice cylinder for you. or a paraboloid. So now I've graphed a paraboloid in 3-dimensional space. Okay, that is new. Okay, that's within the last year or so that this technology is available to maybe 2 years, available to just a person that goes to a website. Okay, so as technology evolves, my Cal 3 students are using this all the time. They come here and they're like, oh, we need to know, what does that plane look like? So here's, we're going to graph this plane. There's a plane. All right, so there's a plane. Do y'all see the plane that cuts through that paraboloid? And then we can try and figure out like, what's the intersection of those two surfaces look like? Okay, so I mean, this is just like different level stuff, right? So we have to, as students and as professors, we have to understand that it's not realistic, at least in my opinion, it's not realistic to make a student go through this grinding process of graphing a function when we can just use technology to help us, right? So I could, go back to Desmos here. I'm
But
sorry.
then we wouldn't learn anything though.
What's that?
I said then we wouldn't learn anything. We'll just get the answers out.
Well, but I'm not saying just the graphing. I'm not saying that. What I'm saying is, if you have something like a function that looks like this, there, right? Then I can use the graphing calculator to help, the graphing utility to help me. But see, if I want that inflection point, that's happening somewhere around here, I'm going to need to take the second derivative and set it equal to 0. Okay, that's what I'm going to need to do. I can do that. I have that tool in my toolbox. Now, to find these local max and mins, the software is actually smart enough to do that for us right now. Right now, it doesn't do inflections. It'll give you any point on here, but it won't tell you where the inflection is. All right. So, yeah. Okay. We're going to move on. All right. So don't do the homework for 4-4. If you'd like, you can watch my video on 4-4 homework if you'd like to see just how involved it is. Go ahead. All right, we have about 10 minutes. This is a good opportunity to introduce you to 4.5, which is, what's that?
I have one question about 4.3.
Yes.
We're just doing polynomials. We're not doing sine functions or any crazy stuff for the test.
Oh no, you're doing sine functions too. Yeah. That's why you need to do the homework.
Okay.
Yeah, make sure you do the homework because you'll see that there are, I can't give you an example of every type of problem. I mean, it's not possible for me to do that. So, yeah, do the homework for 4.3, and I think you'll get a good idea. You know what I would say? I'd say for 4.4? Don't do the homework for 4.4 in terms of sketching the function, but for 4.4, you might look at the problems and at least do what we did today in class. Figure out where it's increasing, decreasing, local max, local min, concave up, concave down, inflections. Like that would be enough. You don't need to do the whole graph. I'm only saying that if you wanted to have a more variety of problems, that's all. Just look at the problems from 4.4.
Sir, for 4.3, do you still want us to just do A and B only?
No, you can do it all now.
Okay.
Yeah, unless it says sketch. If it says sketch something, just ignore it. Yeah, I think it says sketch on part D, but
just ignore it.
Yeah, just ignore that. Okay, so I have 10 minutes. We have reached a very important point in the class where now we can put all of this together to do real life application problems, which means word problems, which means you're going to start freaking out. All right. So optimization problems, the name optimization, when you think of that word optimize, you're trying to make something the most efficient, or optimize means to make it the best it can be. All right. So when we do an optimization problem, we have basic steps that we can follow. Okay, it's a word problem most of the time. So we want to read and understand what the problem is asking us to do. We want to draw pictures when we can. We want to introduce notation. Okay, we might want to call something X, we might want to call something Y, we might want to call something T, whatever. And then very important, we want to determine the variable we want to optimize. We need to figure out what is it that we're trying to optimize, and that is what we call finding the objective function. Then we want to express the variable to be optimized in terms of other variables. I'll explain that when we get to an example. Use the given restrictions in the problem to express the variable to be optimized in terms of a single variable. Again, once we get to a problem, I'll explain this. Last step, use the methods of this section to find the absolute max or absolute min, or to determine local maxes and local mins. So here's a problem, and we don't have enough time to really get into this. This is more of a thinking problem. So let's say that I give you a rectangle, okay? And I tell you that the perimeter of this rectangle has to be 100, okay? The perimeter of the rectangle has to be 100. There are many different ways I can make that, couldn't I? Like I can make my rectangle look like this, where it's 10, 10, 40, 40. That would be 100 feet or 100, right? Let's just say feet. That'd be 100 around the outside, right? So a perimeter of 40, I mean, a perimeter of 100. But what's the area of this thing? Well, I have the computer calculating it for us. It would be 40 times 10, right? So the perimeter of this rectangle is 100. The area is 400. If I reshape this rectangle and still tell you have to have a perimeter of 100, are we going to get the same area no matter what we do? What do you think? If you have to have a perimeter of 100, then if I reshape it, am I having to stay at 400 for the area, or will it be different?
It'll be different.
Different?
Well,
Let's try it. Let's just move it a little bit. Let's do that. How about 16, 16, 34, 34? If you add all those up, it's 100. But now look at the area. It's more, right? It's more area. I could go another way. I could go like to this extreme. I can make this 4, 4, 46, and 46. But now look at the area. The area is only 184. I could go this way, right? Like there, 11, 11, 39, 39. Now the area is 429. So I'm going to start moving it back and forth, and y'all just keep an eye on the area. So if I start at one extreme, the area is really small. And then it starts to grow 300, 400, 500, 600. Oh, wait, it's starting to get smaller, 500. It looks like there was like some optimum, some dimension in here that gave us the most area. Do you understand that? There's some dimension somewhere in here where I get the most area possible. So if the problem says find the maximum area of a rectangular pen if you have 100 feet of fence, then how could we set this up? I'm going to start setting it up for us. And then that way, when we come in next week, we'll have, by the way, this would only appear on your test as a bonus, okay? Because officially we're ending with 4-3. Okay, so this is the way the problem would appear. That's it, just like that. Find the maximum area of a rectangular pen if you only have 100 feet of fence.
I would guess, wouldn't that be 25?
What's that?
Would it be 25? Like,
well, I don't know, maybe. It might be, but we have to show it. We have to prove it. We have to use math. So I want to find the maximum area, right? That's the objective. The objective is to find the maximum area. So let me draw a rectangle, just an arbitrary rectangle. I'm not even going to fix any of the sides. I'm just going to call this X and this Y. Now, do you all agree if I'm trying to find the maximum area, I better come up with a formula for the area? And in this case, the area is just X times Y. We all okay with that so far? Right now, to know the area, you have to know both X and Y, don't you? To calculate the area, I have to give you the X and the Y. However, there is a constraint to this problem. And the constraint is that we only have 100 feet of fence, which means that the perimeter of this can only be, has to be fixed at 100. So what is the perimeter of this rectangle in terms of X and Y? What's the perimeter around it? It'd be
2x plus 2y.
Sure, yeah.
it'd be 2 X's plus 2 Y's, wouldn't it? But that has to be 100. Why is it 100? Because it says we have to use 100 feet of fence. Now I can divide everything by 2 just because that I noticed that I can do that. Right?
Or like
So
that.
to say that the perimeter has to be 100 means that 2x plus 2y has to be 100, which means that x plus y has to be 50. Then what? Sorry?
You can solve for x and then use that in the area equation, or y.
Yeah, so this constraint that we have, okay, this constraint tells us that we could solve this equation for either x or y. I'm going to solve it for y. So I'm just going to move the x to the other side. And now I'm going to use this equation and substitute it in right there for y into my area equation. So my area is now x times y, but y is 50 minus x. And if I distribute the x through, I get 50x minus x squared. So now, if you want to know the area, all you have to know is x, right? Previously, I said to have area, you need both x and y, but because of this constraint, in order to figure out area, now you only need to know what x is, yes? Yes.
Yes.
But that means that the area is a function of x. The area is a function of x, right? It's a function of one variable. And this is a parabola, right? I mean, we know what that would look like if we graphed it. It would be 50x minus x squared. There it is. That's the parabola. And guess what that parabola has on it?
It's got
Look at what it has up here.
Local max.
It has a maximum, doesn't it? This function has a maximum, and we're trying to find the maximum area it can be. So I've got to end class. We're just going to leave this as an open question. We want to take this and we want to find the max, right, that it can be. So we have two different ways we can do this. We can do the closed interval method, or we can find the local max, local min, doing what today and previous class was about. There are two different paths we can travel. The only way you can use a closed interval method is if you can somehow give me some restriction on x here. You have to be able to bound x between two numbers to use the closed interval method. If you can't bound x, then you're not allowed to use the closed interval method. So we have to stop here. Stay tuned. Next class, we get into more of these word problems, and yeah, we'll do optimization. So I will try and send out some sort of review for you in the next day or two that'll help you get ready for the test that is planned for next Thursday, and it'll be over up to 4.3. I am thinking, and I thought about this just the other day, I am thinking of maybe giving you a take-home exam, which would mean I give it to you on Thursday. We have normal class on Thursday. I give you a test on Thursday and I make it due on Tuesday, but that might ruin your weekend. I'm just letting you know, like it might not be.
How big of a test are we talking then?
I mean, it wouldn't be like dramatically bigger than it would be in class. It's just right now for me, class time is more important than test time because we're going to lose a whole day of class, a whole day. I'd rather cover more material than to. So I'm just thinking about it. Let me make a final decision tomorrow.
So are we going to get to Newton's method and antiderivatives, or?
We're definitely doing antiderivatives. I
Okay.
may not do Newton's method, but that's okay because Newton's method is it's for people who are going to do computer science and it's just like a cool result, it's just an algorithm and you can use a computer to run it. It's not important for you going on to Cal 2 or 3 or anything.
So anything covered Tuesday will not be on the exam.
That's right. Okay. Unless it's a take home. I think if it's a take home, then it's all fair game, you know, because then we just talked about it, you have time. I don't want to ruin people's weekends, you know, but if I give a take home, people are going to spend forever on it, even though they shouldn't, you know, they'll take what should have been a 3-hour test and they'll make it like a 17-hour test because you'll keep on going back and looking at it and, you know, and be not sure if it's right.
For how do I word this? What section did we start for this exam is what basically I'm trying to ask.
Yeah, good question. I don't even remember.
Yeah, I don't.
Wasn't it 3.1 or 2.2? I don't know.
Well,
I don't know.
I
I think
let
it's
me bring up
2.1.
let me bring up the exam, the last exam that we had.
What date did we start the exam?
Hold on, I can only handle so many things at one time. Hold on. This was exam 2. So raw derivatives, implicit, related rates. That was the second exam. So that means that this exam would start at 3.1, which really 3.1, 3.2 won't even really be on the test because that was just like, hey, remember exponential and log functions from college algebra? It's really 3.3 is where we started doing derivatives. We had logarithmic differentiation. That was a pretty intense section. Inverse trig functions, we didn't do that, did we? We didn't do 3.4.
No, we didn't do that.
Yeah. So it's really just 3.3 and then 3.7 L'Hopital. You'll understand L'Hopital is a lot.
Mhm.
And then 4.1, 4.2, 4.3.
Feels like so long ago the last exam.
Yeah. Does it seem like it was?
It feels like a long time.
Yeah. March, it was back in March. No. Yeah, was it that long ago? Yeah. It was. Okay, well, that's where we are. Today is the 22nd. See, we're supposed to be starting optimization. Curve sketching usually takes me 2 days to do because the problems take forever. So I do like 2 problems in a class, maybe 3.
Mm-mm.
All right, well, anything else? Stay tuned for a review or something to go off of.
All right. Thank you
Okay.
then.
Yeah, y'all have a good
good
weekend,
weekend.
right? Is it already kind of time for the